Okay, so in these notes, we're going to be looking at graphs of functions and their inverses. And on the front is some information about inverses. Okay, this notation is function notation. So this reads the graphs of f of x, which is the function called f that uses the independent variable x, and its inverse, f inverse of x. So this f with a little -1 symbol, that reads f inverse, and then of the variable x. These are always reflections of each other over the line y equals x. Okay, if the point x comma y is on the graph of the function, then the point y comma x will be on the graph of its inverse, right? Because it reflects over the line y equals x, that means the ordered pairs will switch positions. So the x will become the y and the y will become the x for the inverse. Okay, and then the last one, vocabulary, a function is 1-to-1 if the inverse of the function is also a function. And we'll discuss that more in context as we go through the notes. Okay, so in example 1, we're looking to see if in A, if the function f of x and g of x are inverses. And we're going to check that graphically by sketching each of these functions in a different color on the coordinate plane, and then looking to see if those graphs do have symmetry about the line y equals x, right? If they have symmetry over that diagonal line y equals x, then the graphs are inverses of each other. So if you remember from our last lesson on transformations of parent graphs, we can sketch this graph by recognizing that the type of function is a cubic, right, because of this exponent of 3. The -2 tells me that the parent graph of the cubic went down 2, and then the x plus 4 tells me that it was translated 4 units to the left. So if you recall, the parent graph of the cubic went through 0, 0, 1, 1, and -1, -1, and makes a wiggle shape, right? Now, if I'm going to translate that from 0, 0, the center point, down 2 and to the left 4, then I'm going from the origin down 2 and to the left 1, 2, 3, 4. And so this will be my new center point of the wiggle. Okay, then the A value is 1 and the B is 1. So there's been no reflection and there's been no dilation. So I can use my parent graph anchor points. Right, so now my center point is located at -4, -2, -4, -2. Okay, and then my anchor points are here at -3, -1, and -5, -3. Right, these are my transformed anchor points. Okay, then I can go ahead and sketch that wiggle shape through here, or if you remember, sometimes it's helpful to get an extra ordered pair to get the steepness that you need. So if I put a -2 in here for x, then I would have -2 plus 4 is 2, 2 cubed is 8, minus 2 is 6. So -2, 6 would also be on this graph. And then that gives me enough to go ahead and sketch my f of x. So these would be ordered pairs for f of x. Now g of x, when I look at that one, I'm going to do that one in green. The function g of x is a cube root function, okay, because the index in the radical is a 3. And if you remember from your parent graphs, the cube root function goes through the same 3 anchor points as the cubic, the 0, 0, 1, 1, and -1, -1. But instead of an up and down wiggle, it's a horizontal or side-to-side wiggle shape. Okay, that g of x function has been translated down 4 units and 2 units to the left. So I start at 0, 0, I go down 1, 2, 3, 4, 2 units to the left, puts my new center point here at -2, -4. Okay, The A is 1 and the B is 1, so there's been no reflection and no dilation. So I can use my parent graph slope of 1 to get the next two anchor points, and those then would be located at -1, -3, and at -3, -5. Okay, and again, I can put in a value for x to get another guide point over here. If I notice, though, the ordered pairs, so -4, -2, notice that my x and y switched for the inverse to -2, -4. -3, -1 switched to -1, -3. -5, -3 became -3, -5. So that pattern of them being inverses looks like it's holding. So if I had the point -2, 6 on my f of x, then if these are inverses, when I put 6 in to my g of x, I should get back -2. So let's try that. If I put in 6 for x, 6 plus 2 is 8. The cube root of 8 is 2, minus 4 is -2. So this point 6, -2 is on this graph, and then I can go ahead and sketch that curve. Okay, and so we can see from the position of these graphs, the red and the green are a reflection over that diagonal line y equals x. If I were to fold this half over on top, see how the green and the red would lay on top of each other? So that's what it means to be a reflection over the line y equals x. And we tested from the ordered pairs that for each ordered pair, the x and y switched positions. Right? So that means that these are inverses. Okay. Now when we look at example B, okay, when I go to sketch f of x, the exponent on x is a 1, so this is a linear function, and the linear parent graph goes through 0, 0, 1, 1, and -1, -1, and it graphs a straight line, a diagonal line. Okay, so this parent graph has been shifted up 2 units, and that puts our intercept then, instead of at 0, 0, it will be here at 0, 2, because it went up 2 units. The A is a -3, so I'm going to use that as my slope. So I'm going to go down 1, 2, 3, and to the -3 to the right one, or up 1, 2, 3, and to the left one. Okay, and that line then 1, 2, 3, 1 will go through these points. So my f of x passes through the points -1, 5, 0, 2, and then 1, -1. Okay, those would be my 3 anchor points that corresponded to the parent graph. Okay, now g of x is also linear, and it's gone down -2/3. Now that's not a super helpful y-intercept because our scale is going by ones, not by thirds. So rather than guess where this is located, we're going to go ahead and put in a value for x and find a y that goes with it. So if we want to test that these are inverses, right, we would switch this x and y. So if I were to put in a 2 for my x, right, then I would have -2/3 minus 2/3, which would be -4/3, and that's not a 0. So I can tell right away that these are not going to be inverses. Right? Now to sketch this graph, it would be easier to have ordered pairs that we know would make nice whole numbers. So if I want a value for my g of x to sketch that's going to make a nice whole number point to start with, I'm going to put in something that gets me a whole number answer. So for example, if I made my x -2, that negative and a negative would make a positive 2/3. Minus 2/3 is 0. So the point -2, 0 would be on g of x. So if I go to -2, 0, this would be a nice whole number starting point. Then I can use my a, my slope of -1/3, to go down 1 and to the right 1, 2, 3, or up 1 and to the left 1, 2, 3. Right, I can follow that pattern down 1, 1, 2, 3, and this then would be my line for g of x. So I have anchor points now at -2, 0, at -5, 1, and at 1, -1. Okay, so you can see from these ordered pairs that when I switch the x and y, those do not match up, right? I don't end up with a point 5, -1 on g of x. I don't have a point 2, 0 on g of x. So these are not inverses. Okay, so that would be how we check for inverses graphically. Okay, so I also would like to show you how to use your graphing calculator to see if your two functions f of x and g of x are inverses. So when you turn on your calculator, if you go to y equals, and then we're going to enter f of x into the y1. So we'll have parentheses x plus 4, that's raised to the third power, and then -2. Okay, then we'll press enter, and the g of x we're going to enter in y2. The cube root is in the math menu down here at number 4, and that's the cube root of the quantity x plus 2, and then we'll arrow to get out of the radical, and then -4, and press enter. And then if I want to see if they reflect over the line y equals x, then in my y3 I'm going to enter that line y equals x, and press enter. Okay, now I'm going to go to my zoom menu, and zoom standard is number 6. Okay, that's a -10 to 10 in both directions. Or number 5 is zoom square, which will sort of square up the window a little bit so that it's not quite so distorted. So I'm going to go ahead and do zoom square. And then there's my f of x. Here is g of x. And then there is my, my diagonal line y equals x. So it looks visually as if these are inverses, that they have that reflection over the line y equals x. But to verify that, we really should check some ordered pairs. So if I hit trace, up in the corner here, we'll see that currently we're dealing with the y1, which is the cubic function, the x plus 4 quantity cubed minus 2. So if I enter in a point, like if I put in from my list of ordered pairs here, -4 for my x, when I press enter, I should get back -2, right? And I do. So that point -4, -2 is on the graph of f of x. Now, if I use my arrow to toggle down, right, now you'll see up in the corner that I'm looking at the y2, which is my cube root graph. Okay, so when I type in -2 for my x, I'm trying to verify that I get the -4, because remember, if they are inverses, the x and y coordinates will switch positions. So I press enter, and sure enough, there is my -4. So I verified that the point -2, -4 is on g of x, and that -4, -2 was on f of x. So that showed that those ordered pairs were reversed. Okay, now if I go back to my y equals and I want to check, for example, b, then I can hit clear, and I'm going to replace that y1 with -3x plus 2. And I'm going to replace my y2 by hitting clear with negative 1/3 x minus 2/3. Right, that's my g of x. My line of symmetry, y equals x, can stay the same. And then I'll go to my graph, and there's my f of x, there's my g of x, there's the line y equals x, and you can see from this point of intersection here, and just visually, right, if I was to reflect over the line y equals x, these are not inverses. Right, if you wanted to verify that with ordered pairs, you would hit trace. Notice that we're in y1, which is the negative 3x plus 2, and I type in negative 1 and get back 5. Now if I use the arrow to toggle down to y2, right, negative 1/3 x minus 2/3, if I type in that negative 5, I should, if they were inverses, or sorry, not negative 5, if I type in 5, I should, if they're inverses, get back a negative 1, but I don't. So I can see there that these are not inverses graphically.